Hi, everybody. Thanks to the organizers for inviting us to speak here today. My name is Michael Craig, and I'm a machine learning scientist at GTN. GTN is a startup based here in London, and we kind of combine methods from quantum chemistry and quantum physics with the newest machine learning algorithms in order to improve the drug discovery process. And everyone that works there is kind of like everyone has a basic research background, and we have people from quantum physics, from machine learning, biochemistry. My background is really kind of between the machine learning and biochemistry, so that's where I'll focus the talk today. I'll start by just talking to you a bit about some of the models that we're using. Talk about specifically about graph convolutional neural networks. Then I'll go into some of the open source tools that we use and some of the open source data sets. Do a quick demo, and then show some preliminary results on the toxicology data set that we've been working on for a little while. So I'll start with just the obligatory deep learning slide that all machine learning talks tend to have. So the deep learning can be applied to many different data domains, but it's really specifically very good with image recognition. So these data sets like MNIST, looking at handwritten digits, and also image recognition with ImageNet. Convolutional neural networks have been shown to perform very well in these kinds of data sets. Natural language processing with recurrent neural networks as well. And when combined with a Monte Carlo tree decision algorithms, you can play games with them even. But one similarity that all of these data sets have, at least the two-dimensional ones, is that they all work on regular grids. So the kind of basics of how this convolutional neural network works is that they all operate on regular grids and update based on pixel values. So say you want to kind of stack a bunch of these convolutional layers on top of each other and feed in images of faces. At the most shallow layers of the convolutional neural network, you're going to have relatively simple features being extracted. And that's kind of the basics of how a CNN works. You're trying to extract these hierarchical feature representations. And as you get deeper into the network, the features become more complicated. So again, at these shallow layers, you have very basic features like edges, shading, curves, things like this. As you get deeper, you have slightly more complicated features being extracted. Like in the case of faces, you'll have something like noses or ears, eyes, things like that. And as you get deeper, you have more complete looking faces or features in this case, these terrifying little ghost faces that are at the deepest portions of the neural network. But the issue with these is that many real-life data sets are not organized on these regular grids. So there's been research over the past few years aimed at trying to generalize convolutional neural networks to work with data that's based on modeling the data as a graph. And in the simplest sense, a graph is just a pairwise relationship between objects. And kind of simple examples of these are social networks, where you might have nodes being individuals and edges being some kind of relationship between those two people. Road maps are a good example of something you can model as a graph. Various biological networks, like brain networks and protein interaction networks, are often modeled as graphs. And what's most relevant to us are molecules. So these kind of representations of molecules are often depicted as graphs. So the goal of what we're trying to do is trying to generalize these kind of basic convolutions to work on molecular graphs. And with the standard convolutional network, you can see that you're kind of sliding this, you're taking a window and sliding it across the image so that you're looking at every portion of the input image, and you're extracting these hierarchical features from the image. With a graph, you're doing something slightly different. So you're going to each node in the graph, and you're combining information from its neighboring nodes. And that's kind of the equivalent of a convolution in a graph sense. And as you go deeper into the graph convolutional network, you start combining information from a larger and larger neighborhood around that node. In the literature, this is referred to as message passing, so people have started calling these message passing neural networks. Here's just an example of how you can kind of model a molecule as a graph and then as an adjacency matrix. The way we actually use these graph convolutional networks is we have two different inputs for them. So we have the adjacency matrix for the molecule, and also a feature matrix. And this feature matrix contains a feature vector associated with each of the nodes in the graph. An important point to make here is that you can create many different adjacency matrices from the same graph. So there's actually a summing function at the end of after the final layer, which makes the model invariant to permutation of node labeling, which makes it slightly different from a standard convolutional network. This would be the kind of most basic layer propagation rule you could construct with this, which is already somewhat powerful. And here you just have your weight matrix and a nonlinear activation function like a reloop. But there's kind of two problems with this, this propagation rule. The first is that multiplication with A means that you're summing features from adjacent nodes, but not from the node itself. So the simple solution you have there is just adding the identity matrix to the adjacency matrix, which forces it to sum features from the node that you're applying the convolution to. The second issue is that A is not normalized, meaning that multiplication can lead to scale changes with the feature vectors. And in this sense, if you have very highly connected graphs, so if individual nodes have a very high degree, this can result in these very large changes in scale. For our purposes, this isn't a very big issue because atoms can't really have a degree higher than 4. But when you're looking at social networks or biological networks, these you can have a very high degree for individual nodes. So applying a symmetric normalization, the degree matrix allows you to normalize that and take care of that. So this is the actual final layer propagation rule you end up with. Just to give a somewhat cartoon example of actually how this works. So if you take a very simple graph like this here, and you want to apply this rule to this node in black, each one of these nodes has a feature vector associated with it, each neighboring node. And what you're doing is summing up or combining all of the feature vectors from those nodes, from the adjacent nodes, and also from the node itself. So that's just kind of an illustration of how it works. This is some just kind of TensorFlow, very simple cartoon code, just to kind of show you the different pieces of one of these networks and to show you how how you can put this layer propagation rule in. So first, you're just instantiating your tensors and your weight matrix. Right here is the actual layer propagation rule. So this is this little equation that we're applying. Down here, we're calculating loss and optimizing, and finally just training the data, or training the model rather. So just kind of a very simple example of how this could be used. And it's important to point out that if you can get your data into a format, into a graphical format, then it's relatively easy to apply these kinds of convolutional networks to it. There's a lot of open source software on GitHub that allows you to do that pretty easily. To kind of just do like a step through all of these the actual like processing of the information. So you're starting with just modeling your molecule as a graph, and in this case your atoms are the nodes, and the bonds between the atoms are edges. At each layer, you're passing messages between adjacent nodes, and as you get deeper into the network, the larger the neighborhood gets. So you're sharing information across eventually the entire molecular graph. And after the final convolutional layer, the feature vectors are summed across all of the atoms, and this makes the model invariant to permutation of node labels. This is an important point, just because in a standard convolutional network, what you'll typically see done is people will input rotated images to try to infer this rotational invariance for features. But you can't really do the same thing with graphs. So you can't just relabel all of the nodes how many times you want and create new adjacency matrices and use these as input, because this is kind of an endless process and won't end up working. So this is something we have to deal with, this permutation invariance to the node labels. To transition a little bit, to talk more broadly about the different open source tools we have available to you in drug discovery, if you're interested in looking into this field. One of them is RDKIT. So RDKIT is a chemoinformatics toolbox that's in Python and C++. This can give you basic chemical information and also allows you to easily work with chemical data in Python. So there's just a load of functions that allow you to manipulate chemical or molecules in different ways and get certain molecular properties from them as well. And then there's these two very large databases that we use as well. The first is ChEMBL. This is specifically for drugs and drug-like molecules. This contains about 1.4 million compounds. In this case, you have 1.4 million molecules and I think several thousand different targets for those molecules. So this could be anything from how well it binds to a particular ion receptor or how soluble it is or something like this. All these different measures associated with the molecules. And PubChem is a bit more general. So this is much larger. There's about 96 million compounds in it, but it's not specific to drug-like molecules. So if you're interested in material science or other areas like that, you can find molecules in there. To curate those molecules, we use this database filtering tool, KNIME, which allows you to actually extract information from these databases. And this is where having an organic chemist on the team is really useful because they can direct you towards what kinds of questions are interesting and what kinds of assays can be used to ask certain questions. So combining KNIME with PubChem and then some domain knowledge allows us to curate these databases in specific ways to ask specific questions about various molecules. And most relevant for this talk is this tool called deepchem. So this is developed at Stanford. And it's an open source deep learning platform for chemistry generally, and it's really geared toward drug discovery. And this is everything from basic data loading functions, provides lots of data sets that are contained within ChEMBL. A very easy way to just interface with that. Pre-processing tools and also a lot of graph convolutional models, different versions of graph models, and a lot of wrappers for scikit-learn as well, so you can use scikit models in this pretty easily too. And lots of evaluation functions and things like this. So yeah, deepchem is a really useful tool for us. So now I'll show you a little bit of deepchem to show you kind of how easy it is if you want to get started and actually see how to run one of these models in deepchem. So here, obviously just loading a bunch of stuff. Here, this is the actual data set that we're loading here. Is it working? There we go. Yeah, here's the actual data set that we're loading. See if that'll work. There we go. And here's the loading of this data set. Down here, we're just defining a metric. So what we're trying to do with this data set, so this data set provides solubility measures. So this is how well a particular molecule can dissolve into water, essentially. And what we want to do is predict how well it can do that. And this is very relevant for drug discovery in that you want to make sure that your molecule will dissolve well in blood and various things. And what we do is just correlate these two measures. So correlate our predicted value with the real value and just take the R squared. Down here, we're defining our actual model, so this GraphCom tensor graph, which I'll show you a little bit of kind of like the guts of it and how it works in a second. And here we're fitting the model. It's running. So I'll let that run for a second and show you how it works. So this is the actual implementation of GraphConv in deepchem, which is a bit more complicated than the one I showed you previously. So up here you're defining your atom feature vectors and your adjacency matrix. And there's also some atom indexing functions as well, which is really just to make these more computationally efficient. So there's just kind of specifics of how deepchem works itself. And down here is the actual body of the graph convolutional network. So you can see each graph convolutional layer here, batch normalization, pooling layers. I think there's 2 in this, yeah. And then there's this readout graph gather function at the end is what's summing across all of the actual nodes after the last convolutional layer. So we'll see how far we've made it. Yep. So we have a training accuracy of 0.95, or training R squared of 0.95, and a validation of 0.84 and a test of 0.88. So deepchem will split the data for you in various ways too, which is very convenient. You can apply a lot of different splits to it to make the problem harder or easier depending on what you're trying to do. And here's just the values correlated with each other. So predicted, real on the x-axis and predicted on the y. So there's very high correlation, and this is the test data set. And this is approaching state of the art. If you, do various kinds of hyperparameter optimization or changing around how the actual model that you're using you can improve this. But this is just completely vanilla implementation of it. So yeah, now I'll talk a bit about kind of another problem that we're working on. So this is another data set called Tox21, and this is a large data set of molecules and various toxicity measures. So it's really important that at early stages in drug development that you are testing to make sure the novel molecules you're generating are not toxic. So one of the assays in this data set is an ion channel in your heart. So if you have high binding affinity with a particular drug you're trying to develop with this ion, then you're really developing a poison. So you want to make sure you stop that at a very early stage of development. And there's a lot of effort that goes into screening out these molecules at these early stages. And this data set was a result of the collaboration between several large scientific organizations that pooled together all of this data that they have about the toxicity of various molecules. And the goal is really to get away from toxicology screening and experimental studies in animal models and such, and towards a more computational and automated approach. Yeah, and again, this particular data set contains 12 different assays, each with a binding affinity for a particular receptor. Another point to make here too is something called multitask learning. This is another tool that deepchem provides for you. It allows you to train the same model using many different data sets. And essentially it allows you to kind of leverage certain assays that have a large amount of data, and they can help improve results on assays that have, say, a smaller amount of data or something like this. And this is particularly useful in domains like this, where access to data is quite difficult, and finding large databases is rather difficult. So anything you can do to squeeze out a few extra points is definitely something worth doing. And deepchem also provides a simple wrapper for this to allow you to use it with scikit-learn models as well. So I'll just show you basic results we have for that. So we use XGBoost as a baseline model. So this is a tree ensemble method, which performs relatively well on these tasks out of the box. So I'm just showing ROC curves for 3 of the 12 tasks here, and showing results down here for GraphCom. So this is, again, the same kind of very simple implementation of GraphCom. And you can see, just based on the AUC, that you get a lot more power out of these graph convolutional networks as opposed to the tree-based methods. So yeah, so to sum it up, I mean, there's many different applications of machine learning and drug discovery. This is like an endless number of areas where this can be applied to, and I think looking at graph convolutional neural networks in particular is really interesting, and modeling molecules as graphs is an interesting approach to featurizing data sets. And there's access to a huge amount of this data online, and also many of these open source packages in Python. Finally, I just want to mention very briefly that we're hiring a head of machine learning, hiring a head of research engineering right now, to work with all of these fine people. And if you're interested, you can come see me, Vid, or Lawrence, I think, is here as well to talk about that. So yeah, thank you very much for your time.
We have time for a couple of questions.
You mentioned a little about your hyperparameters. How much time and how do you go about kind of investigating which hyperparameters are the best ones to choose?
Yeah, I mean that's something that we're working on all the time. So using Bayesian optimization approaches is one thing we've done in the past, which seems to work relatively well. Also, currently we're exploring hyperband, the hyperband algorithm bit, which I think was released last year. So yeah, trying to use all the tools we can to optimize the hyperparameters in this automated way. So yeah, that's our approach. Yeah.
Does attention make sense in graphs? Has it been tried?
Yeah. So there's work by Thomas Kiff and Max Welling from the University of Amsterdam. I think they have a recent paper on ICLR about this. applying attention to graphs. So yeah, I don't know. I haven't read the paper or anything, but I know it's an area of interest, definitely.
Speaking of variant permutations, maybe variant to chirality as well?
That's a good question. I'm not sure, but possibly. Yeah, I have to talk to one of the chemists about that. But yeah, it's an interesting question.
Hi, thank you for the talk. I've got a question about gradient boosting in one of the last slides. So you mentioned that the number of degrees of freedom is limited. So I was just wondering, is the decision tree, how would you just describe the decision tree? Is it more deep or is it more wide in your case?
So I think we use 500 trees for this, but I'm not sure actually. But yeah, I mean we haven't optimized hyperparameters or anything for XGBoost and as much detail as GraphCon. So there could be definitely something worth exploring though. Yeah.
Yeah, the front.
Oh yeah.
I was just going to ask, if you strip out the final layer in your neural net and now you have some sort of embedding of your graphs, do you have any insights into what happens in that space as you kind of move around in terms of chemical properties or something?
That's a very interesting question too. Yeah, I'm not entirely sure. But yeah, so I mean I mean maybe we could talk to one of the chemists or the physicists here. But yeah, it's an interesting question.
So how applicable is this towards biology, towards large molecules?
To larger molecules?
So proteins and...
So it depends on what kind of data you have. So protein interaction networks are kind of different from this kind of like modeling an individual molecule. But I know there's definitely some work at Stanford that looks specifically at protein interaction networks and applying these methods to them. So yeah, I think they're very applicable.
One last question. Oh, well, let's thank Michael again.